All right. Welcome everyone to another Common Lisp study group. I'm your host Ram Vedam with Atlanta Functional Programming. Today we're going to be continuing our journey through the Lisp Interface Library as we have been doing the last couple of weeks. Specifically, we're going to be continuing our discussion on API design. Last week, as many of you have seen, or those of you who have not, just rewatch last week's video on this. We implemented the sequence and completed our implementation of the sequence interface following the principles of how to define a custom interface, a concrete interface that is, to leverage the interface passing style in the Lisp Interface Library. Before I go further on some of our discussions today, a couple of announcements. One, for those of you who are also part of, and those of you who are interested in learning the Haskell programming language, Atlanta Functional Programming has begun hosting the Haskell study group, which occurs weekly on Sundays from 1:30 p.m. to 3 p.m. Eastern Time. This is a study group that is going to not only explore the Haskell programming language itself, but we are going to be discussing practical engineering concerns like, setting up build systems, how to use Docker to create production level images for your Haskell code, differences between Cabal and Stack, and so forth. Tomorrow, our episode is going to be mainly exploring how to set up your environment to learn the Haskell programming language, and we're going to be introducing the basics of the Haskell programming language, data types, how to leverage your REPL, how to view type information, just basic interactions that you'd want to learn as your Haskell journey begins. So join us tomorrow from 1:30 to 3 p.m. Eastern Time. The stream will be posted 15 minutes prior for those of you who are watching YouTube Live. And for those of you who are joining us on the Hangouts, we will post the announcement in the meetup announcement shortly after today's stream. And hopefully that information will get out to you guys soon. Another announcement, those of you who are enjoying our videos on the Common Lisp Study Group, I'd like to just strongly encourage you guys to like our videos, so this way we can reach out to a much broader audience, thanks to the way YouTube works, because it will be in the search results much more sooner as more people like our videos. If you are wanting to see our videos weekly and want to know what's happening and you're not part of our meetup group, please consider subscribing to the YouTube channel, so that way you can get announcements whenever our live stream goes up, or if we have any other recordings that we put up prior, either after or prior, or during the course of our streaming. That's it. So let's get right down to it. Couple of things from last week's implementation that I had learned shortly after the stream ended, as I was testing a couple of things that we had implemented during the stream. One thing was related to monoid fold and monoid fold star. Now, as many of you probably recall, monoid fold and monoid... is there a question? So,
Ram, you there?
Yeah, can you hear me? Can you hear me? Hello? Can you hear me? Oh. Hello? Can you hear me?
We can hear you now. Yes.
Okay. Well, it looks like there was some issue with my microphone, so I'm assuming that what I just said the last 5 minutes did not actually
Ram, everything was fine on YouTube. Just Hangouts that was YouTube.
Oh, okay, great. Okay, shoot. For a second there, I was just like, so let's get right down to it. Last week, while we were exploring the implementation of our sequences API, a couple of things came out that I ended up realizing after we've, concluded the discussion, specifically related to monoid fold and monoid fold star. Now, as a review for those of us who haven't necessarily looked at the code recently, monoid fold and monoid fold star are one step in the direction of implementing some of the more Haskell-inspired functional constructs inside the Lisp Interface Library using the interface passing style. Monoid specifically, as many of you know, are well, just a brief recap, is a type inside of a pattern inside that was inspired by its implementation in Haskell, where and that in itself is inspired by category theory, is nothing more than basically a closed type that has an associative operation on it and an identity operation on it. Now, types are in this case going to be like a category, and categories tend to have already an identity operation associated with them with the appropriate morphisms. But I don't want to really dig into too much of category theory into this. But just think, if you have a type that's closed under some identity and some sort of associative operation, okay? And I, just as a brief review, gave you guys the associative property here on line 92 in our sequence file, which, by the way, for those of you who are part of our GitHub repository, it is available. I will post it in the YouTube description. Once you have this, you have essentially by definition a monoid. Now, when you are implementing a monoid inside the Lisp Interface Library, monoid itself is an interface, as you can clearly see here, as we have it defined in line 94. But it is an abstract interface, which means you have to implement a concrete version of this guy in order for you to override monoid fold and monoid fold star and any other interface, higher level interface function or a generic function that requires monoid as a parameter. So to do this, what I did was I implemented the sequence monoid. Okay, it's just nothing more than subclass of monoid, and it is a singleton interface. Again, for folks who haven't been with us, who haven't been following our discussion on singleton versus parameter, singleton interfaces are nothing more than at the time of the definition, the Lisp Interface Library generates a concrete singleton instance of this and caches it for later use. So whenever you pass in the sequence monoid to any other function or method, it just gets that singleton instance. It's just like a singleton class in design patterns. All right. You can also have differing versions of the interface. I don't know when that would be the case, to be quite honest with you. I have yet to stumble upon a situation where that is necessary, but the interface passing style does enable you to do that if you need to. So, with that said, with the sequence monoid, I was able to finish up, reconstruct a couple of things. Mainly, the identity of the sequence monoid itself is being used to actually go and determine whether or not we have an identity element defined, actually. Now, in the case of sequences, technically speaking, and this is kind of where my head's at when I define this. I'm not entirely sure where other people's heads are, but For a sequence, the identity element for a sequence would be the empty list. Well, the empty sequence, okay, of some sort. So to illustrate that, I actually went ahead and implemented the ID on line 52 here, and override it for sequence monoid to implement the empty sequence. Now, this is not technically going to work with fold left and fold right as we've defined it. It requires a little bit more massaging, but I went ahead and wrote it the way I did anyway for illustration purposes. But because you need to define the empty sequence as such, and by the way, this method is this ID method, the identity method that is defined as part of the identity interface, which is inside group.lisp in the source code. If you guys want to actually take a look at it. The identity interface itself is an abstract interface, which means we had to actually go and implement the concrete implementation. But since monoid already is a subclass of semigroup and identity, and we've created sequence monoid as being a subclass of monoid, we've, the inheritance hierarchy has taken care of all of that for us. So we could do implementation as such and get an override correctly, and everything will the machinery will hook everything up accordingly. So with this empty sequence being created, this is what I constructed. I went ahead and said, okay, let's grab the the identity element. Let's check to see if it is empty. If it is the empty sequence, then we know that the type, because again, we need, when you're doing a reduction, especially when you're doing a reduction of whether it be a fold left or fold right, regardless of how you implement it, the types all have to match the same. So, although, and I know that this is something missing here, there is no additional paranoid check here that's verifying that everything in the sequence that's being passed in is of the same type. That should technically be in here as a prerequisite check before we actually go and do this. I took it out because it could be fairly expensive, depending upon what the size of the list and the number of elements you have to do a comparison of and all that. And there are functions already available in Common Lisp to allow us to do all and stuff like that. But again, they could be fairly expensive depending on what's being passed in. I went ahead and just assumed that they're all of the same type, and I grabbed the first element as the initial value because, as many of you know, when it comes to identity, regardless of the operation, if you have an argument applied to the identity based on some operation, you always get the original argument back. So x plus ID, where ID is the identity for that given set, will equal x, where the plus sign is some sort of associative operation. So this is the way I kind of implemented this. I basically said, okay, this is going to be the first element of the set, just because we're pretending we've applied the operation already, and then we do the rest as is, and we could call fold left. So this let here that you're seeing is the third argument to fold left, and fold left, as you recall, actually it's the fourth argument. It takes in the foldable interface that you're using, the actual sequence that you're folding on, what is the reduction function, and then what is the seed, which is Lisp interface speak for the initial value for the reduction. And I implemented the same thing for fold left star the same way. When you are defining your, I wanted to bring this up because it illustrates one particular point which we'll be discussing today. When you're defining your monoids or your transformers or anything inside of the Lisp Interface Library, look at whether or not the interface that's being passed in is already a concrete interface or not. Because it very well could be that you just need to pass in the first argument, which is your specific concrete implementation of the top-level interface that the function requires. Not all functions in the Lisp Interface Library requires multiple interfaces to be passed in, but some do. I think the monads one, which we'll touch briefly on later on today, given time, do actually take these as arguments, but do take multiple interfaces as arguments. But don't quote me on that. I just am trying to briefly go off of memory on this. Are there questions on this? I'm showing this to you, you folks. And if you have questions, feel free to post it in the YouTube comments as well as ask questions today. But when you're reading this code later on, and I will add more documentation to this code to illustrate some of the main points on this. You need to understand the reasoning behind why certain structures were written the way they were, and this is kind of my justification of implementing it this way. But this is as generic as it can get when you're using it. Ideally, you should be using interface all ID directly, but given the fact that Lisp is, again, dynamically typed, you don't necessarily know in the reduction whether or not the first element is actually of the same type as all the rest of the elements. This is also why you need to add a precondition check in here to actually really make this solid. Let me just check something here. Okay. No questions on the chat. Okay, cool. So, let's talk about today. The first thing I wanted to bring up is some of our discussion on API design that mainly related to the use of these interfaces. Since we've been, the last couple of weeks, been playing around with interfaces, you see that we're passing in interfaces as first arguments. But it can become a bit cumbersome, especially if you're dealing with a lot of singleton interfaces, because again, the singleton interface is only one occurrence. So there should be a way that our library should be able to determine whether or not the interface exists or not and construct it on the fly. Well, we could certainly do that. An example of this is and we could do that specifically with the interface macro. So to illustrate this, I'm going to pull up my utils file that I started yesterday, and we can go through this today. So with interface is nothing more than a macro that behind the scenes figures out what, for a given interface, all the related methods that interface could be bound to, and it uses some very nice machinery to generate all this code in terms of the generic API that might be available for that interface. And what it does is it creates simple applets for each of them, and then it starts going through and says that, oh, wait a second, by the way, we may or may not use, and that's what declare ignorable is. We may or may not use some of these functions, and if we don't use them, just ignore it. If we do use them, ignore that we're using them. So one of the nice things about the common Lisp declarations for compiler hints is this ignorable kind of function. Additionally, and we talked about this in the past when we were talking about types, Common Lisp allows us to explicitly dictate what can be inlined at the function level. So you could just say declare inline, and it will take all the related functions where appropriate and inline them, so that you can get faster code generated through the Common Lisp compiler. So in this particular case, since I don't have anything defined, you're not going to actually see a lot of that. But I was going to actually go and implement just a simple sort on top of number map and map. This is an adaptation of what is already available. If you look at the paper, the ILC 2012 code, code from the original paper on the Lisp from paper on LIL, and what this code did is it defined a basic sorting function that took a map, it took a list that has an argument. It first converted the list into a map. How do we do that? Well, we remember how we did that before, because there is an A-list map function that could take an A-list and then convert it into a map. Okay? And then we could just call fold right. Well, R. On the map with acons. Where is that map? No. There it is. 1 second. Apropos. Yeah, go with that one. It's already outbound. Just want to make sure, describe. Make sure my alright. So this is the associative pair, and then we could just go and say our initial seed is nil, right? For the more acute observer, one thing should stand out for you. Undefined variable string number map. What? Somebody, I think, has their mic on. I can hear it in the background with the YouTube stream. Could you have yourself on mute, please?
Jay, I think that's you. Bingo.
Okay. Let's see here. For some reason, this is giving me a warning, and I don't necessarily like warnings that would happen. Undefined variable number map tree. We've actually dealt with number map in the past. I'm surprised I'm getting this warning, but we will see what will happen if I use it. Okay, because really it should be all, but so a sort. Oh wait. Board. Oh, did I not load it? Oh, that's the reason why. It was defined, but it wasn't actually loaded. Okay, MRS. Now I'm in there. So, let's see what happens when we pass in name dot AFP and I should actually use 1 because we're not actually doing that to 2021. Actually, I should do this 1 like this. So this way we are actually showing the sort and 3 dot Lisp Interface Library. If I remember correctly, acons, the fold right will. Oops, we're do. Okay, what was the error? Standard function requires at least 2 arguments. Oops. And that's why it's not finding it. Okay, now I see what the problem is. It's not liking my number map. Okay, so let's look at this first and then debug this together. So, interesting. It should have actually injected it into the macro. Should have injected it into the code, but it didn't look like it injected it into the code. Why is that? See here. Okay. Let's try one more thing here. Let's do pure map. No, do stateful map. Supermap I know we've done before in the past. Let me pull up. Pretty sure I have this right. Let me pull up one of our other pieces of code which already has this open. Let me see if I already have it available. Nope. Let's do this. Software projects. This. Okay. Number map. Pure tree numbered map is probably what I probably want to use. Pure tree. Let's see if this actually shows up. Number map. Okay. Let's see if that works. Fold right is called with 3 arguments, but wants exactly 4. Let's see something here. What happens when I do this? Okay. Oops, wrong one. Oh, sorry. That's the one that I wanted. No. This one. Thank you. Okay. So, why is this not actually doing what I expected it to do? It is. So what with interface should be doing, and I've seen this in other code, which is why I'm surprised that this isn't doing it here, is it injects the interface object that we defined, in this case, pure tree number map being an override for list interface all map. And it injects it into each of the API calls that it can see here, has the first argument automatically for you, which allows you to get much simpler, much cleaner implementations of your algorithms this way, because now you don't see your interfaces all over the effing place. However, there is a couple of things about it looks like there's an issue with how it's actually generating this code. So we're gonna have to compile. I'm gonna have to figure out why it's not actually injecting the code the way it should be. And it's probably related to these style warnings here. Let's go to the top. Let's read through this. List interface map, a list map, it calls one argument, Like that is what it's supposed to do. Let me go and look at another Who uses symbols? Hold on, let's see. Okay, hold on. Who calls with interface is probably what I would like to do first. No references found for with interface. Interesting. Okay. Time to go to eShell and do a little digging. Grep. Oh, sorry. Grep with interface. And we'll need the number. Let's do RL. Okay. Oh, that's right. I can actually use. I'll get another buffer here if I do this. Okay. Yeah, that's what I needed. Let's see. Monad, meta class. Stateful map implementation is where I got it from. So if we reduce this guy, we will see that it's doing the same thing. It is not actually injecting the interface into it. It should actually be injecting the interface into the actual reduction. Otherwise, it's going to be causing some problems. For empty, at least. Let me just make sure here. Flet value interface goes in. It defines all the invariants to the monoid fold. Declare normal. Something is not right here. Okay. I will look into why this is like this. This should have caused no problems. Because it is already bound into the map list and we're able to prove it. Oh, I must be using the wrong thing. That's probably why. Go back to this. Sorry, not that, utils. I should probably do this. Pure tree map. I think that's right. Click that. That. I can't read through. Let's resize our window here. See what happens. Still the same for two orders. Okay. Interesting. It might be just that I have to go in and call these using the same. Because this is something that I haven't tried yet. Because I thought I could do this. I changed some of this code this morning when I was looking at it. This is because I thought I could just use the generic versions of these, but it might be that we have to use the pure versions of this for this to actually work. Let's see. CF. Still the same error. Okay. It's not necessarily an error, but we'll see if it throws up when I actually go and try to sort. And as expected, it's going to say it needs to take 2 arguments. Okay, looks like core is not, there's something related to how I have to set up my packages in order for me to actually use this the way it was intended. Because as we can see here, as we saw with map implementation. You can see that it can clearly use with interface to define and inject the code into the interface into the particular function calls. But for some reason it isn't doing that. Let me see if I go and do this. I really don't want to do this just because, as many of you know, I'm kind of in the camp of folks who feel that you should actually just call it directly from the package rather than actually using use. Use is could get you into a situation where you have name conflicts, especially because those things happen at read time. But we'll use it now to see if this actually causes the our package to actually do what it's supposed to do. So first, what I'll do is let me split the window, go here, go into utils, go up here, and let's see, let us do use lil core, use lil interface, pure tree, use for some reason it is giving me that. Let me just do it that way. Okay. Then we do lil pure map. And I don't think I need any other ones. Aha! There's the problem. 4. There must have been some sort of reason why on intern with interface. In fact, let me do this. Let me just restart my Lisp and then get this going again. Okay. And let's do this again. All right. Okay, so now I think I have to do this as well. It looks like use re-export lil pure map. Oh, right. This is only a UIOP thing. UIOP define package. So this way, I could use that. And now I have it. Now let's go into up here, and it still gives me that error. That's weird. That is invalid number of arguments 2. Let's see what this, what this expands to. This now goes and we're getting a different error now because now everything is properly being compiled and loaded. In fact, I feel like I don't need to even do this. I shouldn't have to do this just because I'm declaring them directly. So this should not have to be a problem. Let me do that one more time. So looks like that has to be there. A sort requires how many arguments? It looks like it's calling it correctly. The fold right is being passed in a binary tree. Okay. So there's some weird issue here with the implementation, but it looks like the code is actually getting executed the way the macro is intended. This is just an execution problem with the way I've implemented the acons. Acons requires, that's the reason why. There are 3 arguments to acons, but it's only passed in 2. So my input is wrong. That's the problem. 3, let's do this. 3. Okay. Let's do this. Let's do. Let's do 2, 1, 3, 4, 5. Okay, let's see what happens here. 5 is not a list. So my input is right, but it's not actually being generated the way it was supposed to be. I thought I was reading this right. Acons generate a key datum. No. Okay, I could change this implementation. All right. Instead of using acons, I'm just going to simply do this. Lambda kv car do list. We're just going to convert them into a list of lists. Okay. Let's see what happens here. Let's do this, do that, and you can generate this. There's some weird issue that's happening behind the conversion of acons. Acons is not actually getting what it's expecting to. What I could do is let me see. I could also do lambda kv acons kv, and unfortunately I need the list that's being converted in there in order for this to work, and since I don't have access to that list, it's going to be nil, and this is not going to work anyway. This is going to generate something different. It's going to generate an associative list has a nested structure where each layer of the structure will have one dotted pair, and that's not what we want. But this will still illustrate the point of what I was trying to make. Sorry for the long debugging session there. And that is, you don't necessarily need to pass in your interface objects when you're going through and writing your generic algorithms. In fact, you can actually create a Lisp-style API that looks much like your normal run-of-the-mill Lisp API with keyword arguments, with optional arguments, with refs, what have you, that behind the scenes using Lisp little core with interface can actually call the appropriate generic functions that are already available at your disposal in the interface API. Obviously, in this case, you'd want to make sure that the data structure that you're using that's appropriate, as you're splitting through some stuff, could do the proper reduction the way you're expecting it to, and more importantly, because if I do this, for example, we won't get what we want. But yeah, I'm going to go and change this back to just do list. Let's see what happens here one more time. Nice. Okay, we're getting a little closer there. But I will not waste further time because this example is clean enough here. I'll go ahead and check this guy in. Let's go and continue our discussion on the other thing. There are interfaces inside the Lisp Interface Library that contain methods who implemented their declared functions in the context in which a particular use case applies. All right. An example of this is if you look at some of our EQ functions, and that's probably the best one to really show. Do I have one of those open? I don't think so. Let me just go into my shell and let me go and look at where EQ from equals is defined. Okay. Let's open this guy up. Okay. All right. So there are so in cases like mixins especially, this becomes very apparent. When you are using mixins, oftentimes you want to have a default implementation of a particular generic method that you've already defined, or declared at some point. An example of this is let's say you're defining a concrete version of EQ that specifically handles the case of converting from EQ to equals, all right? And you can clearly see it here. It's just an abstract interface, but it's an abstract interface with a concrete implementation of a function that's specialized on EQ from equals. All right, and all it does is it will call for an EQ function, the equals operator, and as long as it's defined for your two types, because again, equals itself is an operator that has been added in the Lisp Interface Library that takes in an EQ interface object as the first argument and then these two other ones. It will then accordingly do the conversion and actually call the generic function that's specialized on those two, on that particular object. Now, the way you do this is, before you may have remembered when we were defining our interface implementations, right? We've defined the generic functions in the interface itself, and I'll let me just go ahead and do this as a comparison. Sequence. There we go. Let's go back to our sequence implementation. Actually, you know what? I think group is probably a better one. Okay. So when we're defining our interfaces, our abstract interfaces, sometimes we will provide, some generic operations upon which we are, specifying either number of inputs, number of outputs. In this case, ID only takes one input, which is the interface value, and doesn't return anything. Will return one output, which is the identity. But the way the interface method was defined is using this keyword generic arrow, right? It's defined inside the interface itself. There are other ways of doing this that's more class-like in the case of using define interface generic, which oftentimes, if you look at I encourage you to look at the little source code for some examples of this, but I think the best practice based on what I've read in the majority of the code base is, if you're defining an interface, go ahead and use the :generic arrow to actually implement your interfaces with the documentation so that it's all in a single location. Much like that, for your interfaces that need to implement their own default methods, you'd want to use the same idea, but instead of using generic, you'd use method. And that internally macro expands into a define interface method that's specialized on the interface that you passed in. In this case, it's equals from equals. And it will go ahead and generate all that code for you. As you can see here, it's doing multi-layers of actual generation, but ultimately it will create this lambda xy will return essentially this function call for you for your use case, and then you can then use it in your algorithms. These cases are what are called in the interface library has implicit interfaces. They are interfaces that basically behind the scenes will again do all the code generation of passing in the first class interface objects, but from the end user API standpoint, you can look at these mixins and it will feel like they are kind of native to the language and its API. Now, there's one caveat here, and that is, I'm just going through my notes here. The interface argument is going to be bound to the symbol naming the interface. Okay, so when you're actually using this, let's go back to the macro expansion. This binding is happening to the arguments bound to the actual symbol representing what that interface is. Symbols, I'm talking about a Lisp symbol object. There's no special symbol. You might be thinking like self, or in other languages the dis operator, where the interface object is kind of like bound to the methods themselves upon instantiation time. That's because, again, this is all how the class machinery works. It doesn't actually handle this binding cases, it actually treats all of them uniformly. It's a very uniform type dispatch and uses that for doing method combinations in the common Lisp object system itself. So that's just a special feature that's there. But because of that, don't think that when you're defining a method to an EQ function, or when you're defining a method for a specific interface or a mixin, that's a concrete implementation of an interface, that the binding that's happening at runtime is going to be to a sorry, just silencing my phone here. I'm getting buzzed. All right. Don't think that at runtime that interface object that's being passed in is going to be a specific instance of that interface. It's going to probably be already something that's already been predefined, probably as a singleton, probably already been generated when the API was created upon load time. Just giving you that heads up. This is something that I've seen in other examples in the code base. But once you define these kinds of like mixins, you could just use them. And as long as your concrete interfaces adhere to some of the characteristics that mixin requires, everything just falls through, and you can actually use all their code as is. It's actually pretty nice. So we have this. Let me go back to our sequence. So we have the sequence interface that we've defined. We've already implemented all the base implementations of all these super interfaces that required. We made it a singleton. What if, as you're building these interfaces with a lot of algorithms, okay, you'd want to actually make it a globally implicit interface that can be passed around to all of your algorithms. Well, there's a function that's well, I'm not entirely sure if it's a function. I would probably say it's probably it might be a macro, but I haven't actually tried this out. But let's go back to utils actually for this. That allows you to actually define your interface specialized for a specific super interface. All right. So in the case of our sequences, you saw that we had to implement a lot of actually, let me take that back. Let's start with hash tables instead. So Lil, as many of you know, has a hash table implementation. And let's say that you are using hash tables a lot. All right. You can actually end up generating, and let's do that here. Let's create a dumb package here just for the sake of example. Let's say my hash package use CL. We have that. Let's go inside of that package. Okay. So in here, if we wanted to actually create all of our APIs for all the map functions, because we're using hash tables a lot, we could just simply do lil core define interface specialized functions. And what this does is it takes the interface that you're specializing. Okay. So in this case, it's going to be pure map hash. Where is hash table again? Let's do interface all hash table. describe apropos. Actually, why am I doing that? MH. Hash table. Wrong thing. Hash table. That's what I wanted. That's it. Pure hash table. Hash table. Okay. And we then take in our actual map function that we want to create. So we have that takes in a map, because a hash table, if you recall, actually implements the map interface. All right, and we could just do pure map. And what this does here, which is pretty cool, is it will actually generate all of the specializations for this hash table function. So you can now see, boom, we now have every API implemented for the pure hash table that's already been there. That's part of the map interface. Which means that as long as you define your pure hash table in the way it is expected in terms of some of the base operations, you do not need to implement all this code to actually specialize every single function as part of the map interface. You can just get this generated. This is, again, one of the beauties of using Lisp macros, but with this macro especially, it makes writing some of these generic operations a joy. So just thought I'd show this to you so that you guys can take a look at it and see if it, you can use it for your own needs. Their questions? No. All right, cool. Let us do one more thing, which is the final piece of our API exploration, and really the final piece of the Lisp Interface Library. And this is a section that, honestly, that I haven't had too much time to actually go in and explore, just because I've been having some other issues in actually setting some of this stuff up. So we're going to be exploring it together. This is the live coding portion of our discussion, although we've been kind of doing a lot of debugging this current stream. And this is related to one of the core design principles that the Lisp Interface Library was trying to kind of unify. I'm going to put it in the context of folks who used generic libraries or generic programming libraries, especially in C++, because I'm more familiar with that approach. And when I read this, it just reminded me a lot of that. And so I'm going to be using some of that knowledge to at least explain this. So if there are questions, let me know if this makes sense to you. But interfaces at its heart, in terms of the Lisp Interface Library, are essentially what are just meta information. Okay, so by meta information, what I mean is it keeps documentation on the call arguments and the return value conventions for each function that are part of the interface. And you saw that when we were looking at many of these interfaces where they had a :in values. If they are a parameterized interface, you may recall that we had a set of functions that had the inputs and outputs also clearly defined too as well. And this is including a documentation string that kept track of some of that. So the documentation string itself being separate for the case of usage of the API, the ins and out gives you some sort of sense of what an interface is expecting as input and what is it expecting as output. Now, this meta information was slightly different when you looked at the signature of a pure variant of an interface and the stateful variant. So to give an example of this, I think it's probably the easiest way to do this, is to look at pure map versus stateful map. All right. Let me pull that up. Sorry. Where are you? There we go. So we have our map interface, as many of you have seen. Then we have, let's say here, the pure map interface. Okay. And let's pull up the stateful map interface. Okay. So at the outset, you probably will see immediately that that these two interfaces look almost identical. They're, in many cases, are identical in the in that how they are perceived, at least at the signature level. Okay, and this is again one of the goals of what this API was. It's just trying to actually combine pure and stateful, so you don't have to worry about changing from pure to stateful from a function invocation standpoint. Now, that said, some functions, if you look closely, they do change. Specifically, their return values change. And the reason is depending upon if you're pure or stateful, the return values are going to be very different. In the case of, say, pure, we are talking about persistent functional data structures. And that means that the expectation is when you're doing any sort of modification operation, okay, whether it be an insert or a delete or an update, you are actually going to create essentially a copy of the data structure and return that as being the new version with either the new value inserted, deleted, or updated, right? In the case of stateful data structures, these are your run-of-the-mill data structures that we learned in any of our programming languages that we're comfortable with on a day-to-day, mainly in that they are going to modify in place in some cases to optimize for space, only creating new extensions of the data structure when necessary, and they're much more performant in many situations because of the fact that we've already pre-allocated the memory, that we're just modifying what's already been available to us. All right, this is a very important point. We've up until now, we've never actually started looking at these signatures and what they're actually returning or not. But you could clearly see here in the case of, say, insert, we're taking in a map key and value, all right, and we are returning a new map in the case of the pure interface, but we're returning nothing in the case of the stateful interface, all right. Again, with the same thing has a drop. In drop, if you look at drop, we're returning 3 values in the case of the pure version. That is the new map, what the value was that we dropped, and whether or not we've actually found the value inside of the map. And the drop case for modification is, again, it's an in-place modification, so we're not creating a new instance, so we're only returning the dropped value and whether or not it's been found. Okay. This becomes important depending upon how you are, in what cases you're going into the pure state or in the stateful state and vice versa. Now, in the Lisp Interface Library, it gives you the ability, and it's created a model that allows you to emit wrappers, essentially, that can allow you to convert from pure to stateful and stateful to pure. All right. Obviously, pure to stateful has some nice properties. If you're doing pure to stateful to pure, it's going to be isomorphic. In the case sorry, did I? No, a stateful data structure, if you go from stateful to pure and then back to stateful, it will become isomorphic to the original data structure because it looks like you've modified it in place. But if you're doing a pure data structure and you make it into mutating and then back, it's not. Now, I'm going to go back to utils for now. Then I'll go and clean it up. In the Lisp Interface Library, well, let's take a step back. Let's talk about pure interfaces for just a little bit more. When you're talking about pure interfaces that are implementing persistent data structures, okay, as we all know, nothing gets modified, right? But more importantly, we're creating a data structure that has some sort of, updated value for the same object that is being passed into the pure interface as one of the input values that are being passed in. All right. Statefulness, you are dealing with everything in place, and you're not going to modify. You're not going to, create new objects and return them, like I said before. But what we can do is we can actually create, from a pure interface, a stateful interface that may be deduced by putting the persistent values into what's called a mutating box, and then use that to go and update the value, and then return it back into a pure interface. As the name suggests, Lil calls these guys mutating interfaces. Okay, these are interfaces that take in pure interfaces. Okay, they then convert them into a temporary stateful variant. Okay, this is what he calls the mutating box in his paper, right? And then we do our transformations there, do appropriate transformations in the mutating world, and then upon return, we then I'm just going to go ahead and make these into separate bullet points here for folks watching. And again, you'll get these notes when I post them onto GitHub. After these appropriate transformations are done, then what we'll do is we will return a pure version of the transformed stateful object, adhering to the stateful interface at this point. Okay, and this, by the way, if you look at it closely, this here is the same as creating a new object and doing, any sort of transformations. The difference is you've explicitly decided to first promote the pure interface into a stateful interface and then let it go off and do its own transformation, and then only upon the pipeline being done will you go and create a new version of the pure interface. The difference is very subtle but very important. Okay, you are essentially, by doing this pure to stateful transformation up front, okay, you are essentially allowing now optimizations to be thrown out so that modifications can be done in place. A series of modifications can be done in place without having to create a new copy every time. All right, you are minimizing the number of objects that are being created because you've converted this into a stateful version first, and then you're doing all your transformations, and then you're going to go ahead and create the pure version at the very, very end. Very subtle, but very, very important, because in a pure world, every transformation will create a new copy, which means you're going to create a lot of ephemeral garbage. Now, that's not necessarily going to hit you performance-wise nowadays, since a lot of garbage collectors and a lot of Lisp implementations have fairly advanced collectors that are pretty fast at destroying cheap garbage. But it could become a bottleneck over the course of an application when you're doing many, many things, probably many of which are going to be concurrent in nature. Now, so we talked about pure to stateful. What about stateful to pure? From a stateful to pure operation, we have the same kind of idea, but what we'll do is we'll first convert the stateful interface into a pure interface by putting the temporary values, okay, the stateful values, into a box that allows only values to be modified once and not used thereafter, because again, it's a mutable box. The object is then, each object that's part of that collection, that's part of that stateful object, is then extracted and invalidated if there are any new modifications. And if there are any new modifications, it gets invalidated. All right. Again, this is maintaining the purity of the actual pure version of the stateful object. And then when we're done, obviously, we'll go ahead and convert it back. All right. What Little calls it, what this the Lisp interface calls this, it's called a linearized interface. Right. You've actually seen when we were kind of exploring some of the packages in previous episodes, something called transformer/linearized, and so those are the transformations that we're actually talking about. Okay, and again, all this is doing is it first converts each stateful object instance in a stateful object to a pure version. By copying the pure version, by copying the value into what the author calls a linearized box that, upon any modification, invalidates itself and creates a new version of itself with the updated value. This is all done behind the scenes, but this little theory makes it important when you're actually going through some of the transforms that are available in the library, right? So given these two simple principles, these two different types of interface, there's a model of creating effects that a function may have, and there are a couple of examples that that we're going to be just talking through. But there are many ways that you can use this. For example, you might have a function where some input arguments and output values um, are marked as being the interface targeted type. That is the type that the interface is kind of converting to. You might have, and these all again depend on how your functions are defined, but the marking that is kind of brought up for this modeling for the mutating interfaces and linearized interfaces to work together happened when you define your abstract interfaces. So for some reason I did that. Let's go back to map again. Here, these keyword values that you saw here, where there's values or input, and then values that has your output. It is giving you the meta information that's being used by these interfaces in order for them to do their job, the mutating interfaces. So without further ado, I'm just going to go into kind of a simple example here. And I think I've seen one because I didn't want to mess this up, but let's do apropos define interface. That's where it is. Sorry, not apropos, that's the wrong thing. Let's go into eShell and do a grep define mutating interface. There's an example of this. I think they converted it into mutating map. That's the one. Okay. So mutating map, as you can see here, all it does is it creates a new interface, a new concrete interface, all right, subclass of the map interface, but it also is parameterized on the pure map. Okay, so again, remember our definition of defined interface, because defined interface and defined mutating interface is the same set. This actually just expands into a defined interface. First argument is the name of the mutating interface. Second argument is super interfaces. Third argument are the list of parameters that you want to specialize on this interface. In this case, we're specializing on anything that is subclass of pure map. Okay. And what this does is it actually goes and implements mutating versions of each of these interfaces. How does it do it? Well, there's a function that's been defined by the Lisp Interface Library that's called setBoxValue that actually creates that box that we were talking about, that mutating box. This, if we actually go in and describe it, is... Oh, sorry, I did disassemble here. My apologies, not disassemble. Okay. So what this does is, all it does is it generates the code that sets the box instance that's being passed in, and make sure that it actually goes in and creates a new version of that box value that with the new value that's being passed in as a second argument. Empty doesn't do much, by the way. It does it really would shine when we're using something like, say, join list, where we're actually taking the first of the list, we're modifying it, and then we're returning returning f, which is just the map car of f is the box that's the map car of what's it, the list being applied to the box value, right? So here you're seeing kind of an example of how kind of set box value is used for every single one of these methods. Okay, if you're changing a value inside of a collection that's adhering to an interface, this is kind of the function that you'd want to use, right? So what about defined linearized interface? Because we've seen, kind of how pure map interfaces work. This is kind of the same idea. Let me just pull up this and do grep define linearized interface. And we have a same version for maps too as well. All this is already being done inside the transform directory. The transform directory provides a lot of these APIs, so to speak, for doing linearized transformation and mutating transformations. I will briefly just go through and do this, but again, defined linearized interface is the exact opposite, whereas we have set box value for doing updates and modifications to our data structures. Here we have what's called a one-use box value. A one-use box value is a function call that basically checks it's an instance that also has a validation flag. So if we know that something's been invalidated, if the value has been modified, all right, then it will go and recreate itself. All right, that's what that flag is used for. Let me see if I can get to the definition here. Let's see. Value box. These are all functions, but it's an interface box. Okay. Let's see if I can do that. Interface box. And there's different types of boxes, but we're not going to be going through those. I don't think I've seen examples of them being used. I'd have to go and look at see when one might use them or not. But you can see one use box as being defun. I thought it was a defun one value. Yeah, here we go. This guy is just basically using, this is your constructor that goes in and creates a new version of that one use value box. Which brings up one more piece of information that I forgot to mention about the Lisp Interface Library. It shines in this example compared to other ones. A lot of the boxes and thunk boxes and things that that you have constructors around, although they're very Lispish, the constructors themselves, the reason they're the same name as the classes instead of using make, which is a common Lisp best practice when you're creating constructors, you usually have make this typed in order for us to clearly know that you're creating a new instance of that instead of calling make instance directly. It's because of the fact that the reason why the constructors are named as the same as the def classes is because what the author was attempting to do is essentially make these guys as what Haskell calls data constructors. Okay, not necessarily type constructors, but data constructors. They are actually creating a new instance of this type. And if you actually look behind the things, the documentation, they're matching the two so that the type constructor and the data constructor look exactly the same, so that based on the context in which you're using it, you know whether or not you're creating an instance of one thing or you're creating an instance of another thing. Right? I've seen this in other places around the Lisp Interface Library as I've been playing with this, but this is where it really kind of shines, that it really got its inspiration from Haskell type classes when it created some of this stuff. And then it becomes abundantly clear that that if you use these right, the way Haskell kind of expects you to do them, then you get a lot of stuff for free from the Lisp Interface Library. So my suggestion is until you start really digging into the Haskell kind of like stuff, it's probably just use them as is. Use a mutating map, use a mutating box, and then if you need to define your own mutating instances, just copy the patterns that are already available inside mutating map and linearized map, and you will not at all get into a situation where you're not doing something correctly. This is just my suggestion. So, who is actually using some of these things? Well, let's go into, let's go back to mutating. And let's see if def method lookup is already available here. I know it's here, but it's probably in the transform directory itself. Oops. Go to transform. Let's see here. I guess it's going to be in linearize. Let's see here. See what the posh is. Sorry. We looked at this before. Here's look up here. No, it's not. It's not defined here. Interesting. Let me see if I can get the lookup. Sorry. Let me just. Okay, let's see here. Transform as one. Look like transform lookup. Might be in the pure map, probably where it is. Let me try one more thing here. Let's do def method lookup. Okay, never mind. I see what the problem is. I'm looking at this at the wrong thing. It was not actually implemented. This was just available. Okay, so let me go back to, where are you? Box? No, not that. Transform, mutating. This is just creating, this is just the Mac, the functions. And macros for creating mutating methods. This map. Okay. Okay. And is there a lookup here? It's not. Okay. It's being used by the listings. Okay. So, one way of leveraging these mutating interfaces and linearized interfaces is to create cleaned up versions of some of the existing generic functions that we've created by actually wrapping around the method to use a mutating version of that, and then allow the method specialized on the mutating version go and do whatever it needs to do, like create a new version of the particular interface that you're trying to adhere to. Use that to call the top level, say, generic function. Do whatever modifications that you want to do, and then go ahead and depending upon you're using mutating or linearized, create a new instance, or just return values and truths adhering to that particular method function called return values. Now, I don't necessarily have an example of this, just like I said, because this is one section of that I was still trying to wrap my head around. Just because it's a bit like, the idea is fairly straightforward, but as you saw earlier, like, there are some nuances with relation to data constructors that I had to kind of understand, and I'm hoping that I've kind of explained that through some of the code review that we've done. But that said, this actually will complete our exploration into this library specifically, so that way, and I encourage you guys to actually go and look at, again, the processor, the papers that are that I've already put into the YouTube description to actually get a better understanding of some of these concepts. Look into source code to get some of the examples, and honestly play around with it, because the more I play around with it, the more nuances that I'm getting with it. I'm going to probably next time include just some final tidbits, mainly related to some of the built-in monads that are available inside of the Lisp Interface Library. I think we're at a point where I can actually go and show those and use them in a real example. But in terms of the basic concepts of the library, I think today completes the basic overview of what's available inside the Lisp Interface Library. So again, I encourage you guys to go and look at it, take a look at some of these examples. I will submit this code that I just created and post it on the GitHub repository, along with probably some additional examples, because I'm going to try and see if I could come up with a more concrete version of this mutating linearized pipeline. And I'll see you guys next week. That's it for me today. Thank you for joining.